Okay, friends, good morning. So let me recall what we did with nilpotent linear transformations. We proved that if T is a nilpotent linear transformation on a finite dimensional vector space V of dimension n. That means some T power is 0, and if you take n1 as the nilpotency index, that means T power n1 is 0, but no lesser power is 0. And we proved that in such a situation, there is a basis with respect to which the matrix of T can be written as a block diagonal matrix. So Mn1, Mn2, Mnk, where n1 is greater or equal to n2 is greater or equal to nk, and the sum of the ni's is the dimension. And this is also important to recall the form of MR. And MR was of the form where MR, where MR was an R by R matrix, and this matrix was of the form that this had zeros everywhere except on the super diagonal. Except on the super diagonal, and on the super diagonal also we know the entries were all equal and equal to 1. So these were the entries. So all entries are 0 except on the super diagonal, where all entries are equal to 1. Such blocks. Now, thing is that here what we see that on the diagonal also all the 0 entries are there. And super diagonal only contains non-zero entries, and all of these entries are also equal to 1. The point is that now the linear transformation need not be nilpotent. So what can be said about such linear transformations on a finite dimensional vector space? So if all the characteristic roots lie in F, then we can prove something like this, that there is a basis with respect to which the matrix of T will be of a particular form. So I wish to reiterate here this, and you can say that what is called as the basic Jordan block. So Jordan form, that's what we want to do. And so first let me define the Jordan block, or the basic Jordan block. Basic Jordan block with respect to a characteristic root. We assume that the dimension of vector space V over F is n is finite, and T is a linear transformation on this, and lambda be a characteristic root. And lambda be in F a characteristic root. T. So basic Jordan block here with respect to, so with respect to the characteristic root, say lambda in f of t is a square matrix of this form. So you can take, let us say this is J. So J is of the form, or B, J or B, whatever you call. So all entries are 0 except on the diagonal and super diagonal. All diagonal entries are equal to lambda, and all entries on the super diagonal are equal to 1. So this will be of the form like this. Suppose this is R by R, size say R. So in that case, this would be, let us say lambda and then 1 and then 0, 0 like this, and 0, 0. Second row will begin with 0, lambda 1, and so on. And if you look at the last but one here, so this will be 0, 0, 0, 0, and this will be lambda, and this will be 1. And then bottom row will be 0, 0, 0, 0, and last entry will be lambda. So if you see carefully, this is a scalar matrix. So lambda I R plus, now you recall this M R, where what was M R? Same MR is all entries are 0, 0, 0. So R by R, except the entries on the super diagonal are 1. So 0, then 1, 0, 0, 0, 0. Like this. And then you will have 0, 0, 0, and 0, and this will be 0 and 1. So this is the super diagonal. 0, 0, 1, 0, 0, 0. Last row, bottom row would be all zeros only. Okay. So this is what we had seen in the nilpotent linear transformation. All right. So now this can also be seen that this is a matrix where if you write this as alpha ij r by r, and alpha I would be here lambda, alpha I plus 1. They will be 1. These are the entries which are for super diagonal, and alpha ij, all other remaining entries will be 0. So this will be for all j which is different from I and different from I plus 1. This is for all I. This is also for all I. This is 0 to R. R. This is 0, 1, 2, and R minus 1. Like that. So a basic Jordan block corresponding to a characteristic root, let us say lambda, in F of the linear transformation T on V, is a square matrix, say of size R, means R by R. All entries are 0 except on the diagonal and super diagonal. All diagonal entries are equal to lambda, and all super diagonal entries are equal to 1. What we want to prove is this theorem. So we want to prove this theorem. So let us say T be a linear transformation. Ah, First of all, the dimension of V over F be finite. So let us say dimension of V over F be n finite. This whole thing that we are doing is for finite dimensional vector spaces. And T and T be a linear transformation on V have all of its characteristic roots in F. If lambda 1, lambda 2, say lambda k in F are all the characteristic roots, of T, then there exists a basis, say B, for V over F, with respect to which, or in which, so with respect to which the matrix of T, matrix of T is of the form. So the TB with respect to this will be of the form this. J1, J2, diagonal, block diagonal matrix, JK, n by n. Where each Ji is of the form, each Ji is of the form. What is the form of Ji? Like this. Again, a block diagonal matrix corresponding to this I. Let me put Bi1, Bi2, Bi, Ri. Yeah. Okay, so each and what these BIs are, where each of these is for every I, for every I, for every I. 1 to K. 1 to K. And where each Bij is of the form, where each Bij J1 to Ri, J1 to Ri is a basic Jordan block. Is a basic Jordan block with respect to the characteristic root lambda I. So such a result we want to prove. Now you can see that if T is nilpotent, all of its characteristic roots are equal and equal to 0, and 0 is always there in any field. So in case of T being nilpotent, the matrix of T with respect to some basis which can be found out is of the form J1, J2, Jk. And each Ji is of the form Bi1, Bi2, Bik, and where each Bi or I is of the form, all entries are 0 except on the diagonal and super diagonal. And the diagonal consists of characteristic roots. Since for nilpotent linear transformation, all the characteristic roots are equal and equal to 0. So diagonal also will be 0 in that case. So this Ji for nilpotent linear transformation will consist of Jordan blocks. So that will be all entries zeros and one on the super diagonal only. And that's what precisely we had already proved. So this we want to prove. And we also proved about the two nilpotent linear transformations when they would be equal if and only if they have the same invariants, which also in terms of the matrices were equivalent to the two matrices will be equivalent if and only if they can be brought into the same form. And that form was the Jordan form. Only thing we did not say at that time was Jordan. Equivalently, if they have same invariants. So like that also we would like to prove here as well. Okay, so to prove this theorem, we shall need a few workout beforehand. So we go back now again to a few things that we need now. So let us say we be a finite dimensional. So proof will consist of some results that we need to prove now. So let us take and always dimension of V over F, say n be finite, and T. So for now, so this is ये क्या हो गया भाई? हाँ, पता चला गया. ये नया खुल जाता क्या बाहर? ले आएंगे क्या? उसको छोड़ नया ही सेट. Okay, so for proof, so let us take V be a finite dimensional vector space. So dimension is n. T a linear transformation here. And let us say W be a subspace. So let us take W be a subspace of V. Be a T invariant subspace. T invariant subspace. Subspace. T invariant means that is WT is contained in W. All right, so let us take this T is V to V, and let us take TW to be the restriction of T on W. That means what? That Vt and V of T W will be same for all V in W. So this TW therefore becomes a vector space W, and this is a linear transformation of W. Now what more we can see here is that if you take TW square and observe that TW square on every element in W, W, this will be W, TW, TW. So this is same as because this is T invariant, so WTW is in W, is WTW This is n under T. And this is same as WT T. This is same as WT square. So this is for all W and W. So that is for all W and W. So that makes that TW square is same as T square restricted to W. And so likewise, you can also prove that Tk here power k, no? So TW power k is same as T power k restricted to W for every k 1, 2, so whatever. Also, you can take if there are two linear transformations, T1 and T2, which are restricted to W, their sum also will be restricted to W. Also, say you have S also. Also, if S also is a linear transformation here, then T plus S restricted on W is TW plus SW. This can be combined into. So, in fact, this leads to proving that if Qx is a polynomial, let us take alpha naught plus alpha 1x, say alpha m x m, be a polynomial here in fx, then qt will be what? Alpha naught I, alpha 1 t, and so on, and alpha m t m is also a linear transformation here. So what you can easily see here that this VQT, so VQT here for every W, okay, and for every W in W, take W down there for your, this is same as. So V under this alpha naught I, alpha 1 T, alpha m T m, and this is W, and this is same as. So it's W, and then this is alpha naught I plus W alpha 1 T, W alpha m T m, alpha naught, and this W I is W only, and plus alpha 1 WT, alpha m WTM. This is same as, so when W is W, so this is alpha naught, and this is W. So this is W, and plus this same as alpha 1, and WT and T restricted on W, they will be same. W and T restricted to W will be same. Alpha m W under this T restricted to W power m. So this is power m. This is power m. This. So this you can see that this is a polynomial here w under alpha naught I plus alpha 1 tw, and this is alpha m tw m. So this is w q t, and this is w. So when this is restricted to this, so w q t is restricted to w, then this is same as that w. So, and this is for true for all w and w. So that makes that qt polynomial restricted to w is same as the polynomial in tw. And therefore, what happens that if qt is 0, then this qtw is also 0. So if qt is 0, there is a polynomial satisfied by t, then its restriction also will satisfy the same polynomial. qtw will also be 0. And naturally, if p wx is the minimal polynomial here, pw, then this will divide px. And so if the minimal polynomial of t AFV is say px is px, and pw x here in fx is the minimal polynomial of say tw, which is restriction of t and w, and this is in AFW. Then this PW will divide PX for every T invariant subspace W of V. Very nice. So this is what we have. All right. What more we can prove is this. Now, what more we can prove? In fact, we can prove this. We can prove more. So what we can prove is a lemma that if V is a direct sum of two subspaces, say V1 and V2, where V1 direct sum, where V1, V2 are two T invariant subspaces of V, and T1, T2 be the restriction. T1 is the restriction of T on V1, P2 is the restriction of T on V2. And what more, we have, let us say, P1x in fx be the minimal polynomial, of T1, and P2x is the minimal polynomial of T2. Then the minimal polynomial of T. Then Px, the minimal polynomial of T is their LCM. Is the LCM of P1 and P2. This is what it is. Interesting. So these direct sum of two T invariant subspaces, say V1, V2, and T1, T2 are their restrictions correspondingly on V1, V2. P1, P2 be their minimal polynomials. Then the minimal polynomial of T is actually the LCM of these two minimal polynomials. The proof is rather straight. So we can prove this. So since P is the minimal polynomial here of T, so Px here is the minimal polynomial. Is the minimal polynomial of T implies that Pt is 0. Pt is 0, so we know that just now we have proved that P of T1 is the restriction here is also 0, and that will make that P1 is dividing Px. Just now we had proved exactly that P1 will divide P, and similarly P2x also will divide Px, and that means if you have this say the LCM, then this but then the LCM say Lx of P1x P2x will also divide ओके अरे आई होती है कि वी होती है मेरे सब गड़बड़ी होता जा रहा है क्या will also divide px converse is simple so conversely v is v1 direct sum v2 so implies that every v can be written as v1 plus v2 uniquely for some uniquely determined v1 in v1 and v2 in v2. Okay. Now, what we see here Okay, so every element V in V can be written as the sum of V1 plus V2. V1 and V2 are uniquely determined for a given V. And this also will give us that, so V under this LT, L is the linear, this LCM of this, and this LT, this will be same as V1 under LT plus V2 under LT, where Lx is the LCM of this P1 and P2. P1x, P2 x. So this LT is a linear transformation, implies this LT is a linear transformation on B. Okay, since what we know that P1 and P2 they divide L, and therefore this V1 LT will be 0 and V2 LT will also be 0. So we get since P1 T1 is 0 and P2 T2 is 0. So this when you restrict so this LT1, this is will be 0 and LT2 will also be 0. So this will mean that LT1 is 0, L of T2 will also be 0. Since P1 divides Lx, P2 also divides this Lx, and therefore VLT will be 0. This forces that so V here VLT will be 0 for every V in V. So LT will be 0. So that makes that LT will be 0. But that means that Px divides Lx. That is Px divides LCM of P1 and P2. Okay, and yes, Px converse already we have already proved is the LCM of this P1x and P2x. You can extend this as a corollary to more. Instead of just having the direct sum of two subspaces, if V is the direct sum of some say k number of where each Vi is a T invariant subspace of V, and Pi x in fx is the minimal polynomial of say Ti What is Ti? Ti is T restricted on Vi for each I. 1, 2, say K. Then what will happen? That the minimal polynomial of T, say Px, the LCM of P1, P2, Pkx. So this you can prove. Just you can extend this. Now let us do something more. Now let us do something more here. Okay, let us say Px the minimal polynomial. So this is now with theorem. So let us take once again that V be finite dimensional, T be a linear transformation, dimension of V over F be n finite, T a linear transformation here, Px in Fx be the minimal polynomial, the minimal polynomial of T be of the form. Be of the form. So this is a polynomial. So you can write this as the product of irreducible factors. So we can assume that this is Px equal to Px equal to the Q1x power L1, Q2x power L2, Qkx power Lk, where each Li is positive and Qix is irreducible. Over F. Irreducible polynomial, a polynomial fx is said to be irreducible if it cannot be factored as a product of two polynomials of positive degree. All right, further let us take V1, say for example, V1 to be the set of all vectors in V such that V Q1T power L1, this is 0. And V2 will be all vectors in V such that V under Q2T power L2 is 0. And so on. So Vj would be what? All V in V such that V Qj T Lj is 0. For every j, so for every j 1 to k. Then what will happen? Then few things we can observe. So number 1, each Vi is a subspace. Number 2 is a T invariant subspace. Subspace. This T invariant subspace. That means a subspace. T invariant subspace. That means And if Ti is the restriction of, say Vi, if Ti is the restriction of T on Vi, then each Vi is of course not zero, and V is the direct sum. Okay, and if Pix is the minimal polynomial of Ti, if Pix in Fx, the minimal polynomial of Ti, then this actually is nothing but Qix power Li. For every I, 1, 2, up to K. Every I, 1, 2, up to K. So this is what? Fifth. So these are few simple observations we want to prove. So quickly we can see some of them, and then tomorrow we shall look at the other. Okay, so proof. Number one, that recall that this what is Vj. So Vj is all V in V, such that V Qj T power Lj power. This is power Lj. This is 0. Now this is a subspace of V. Since alpha u plus beta v, if you take alpha beta in F, and is under Qj of TLJ is same as alpha u q j t, and this is Lj plus beta v under QJT Lj. And naturally this is 0, so this is alpha 0 plus beta 0, so this is 0. And that forces that alpha u plus beta v is in Vj for every uv in Vj, and for every alpha beta here in F. So this proves that they are subspaces. And the second thing is also straightforward, that each Vj is T invariant. So for this, you can see that V belong to Vj, suppose, then what will happen? VQJT and this under Lj will be 0. And this is same as can see that V T Q J L J, this also will be 0. If you, so this will be, so this will be V T, so V T, then you have here, this is Q J T power Lj. This is same as, because T and T powers, they commute. T also commutes with identity. So T and this will be exchanged. So this is V Q, J, T, L, J, T. This is 0, so this is 0. So that makes that VT is also in. VT is also in J. So that makes that Vj is T invariant. So far so good. The third thing is also rather pretty simple. In fact, all are very easy. So the third thing is that Vi is non-zero. Vi is not 0. So if because V is the direct sum, so if K is 1, in that case V and V1 will be same and V is not 0, so V1 also will not be 0. So if K is 1, then V and V1 will be same and is not 0. And what is Px? Px is Q1x L1, Q2x L2, QKX LK. You can define say H1x as Px divided by your Q1x L1, Q1x L1. So you can define this for every j. So say Hj, so Hjx will be this. So this will be Qx Lj. So that means all will be there. For j is equal to 1 to k. Only thing Qj x Lj will not be. Okay. Or so that makes that Px here is Hjx and Qjx power Lj for every j 1 to say k. Now if k1 is greater than 1, so if k1 is greater than 1, then what will happen? Hix will not be equal to Px. Naturally, because there is some factor there. So this will make that HIT will not be 0. Since Hix divides Px. And Px is what? Is the minimal polynomial. The minimal polynomial of T. So there exists therefore there exists a V in V such that VHIT is not 0. Such that W you call it. So V under HIT is not 0. Now W is in V. For you can see that W under QITLI is what? So this is equal to, replace for W, so this is VHIT and this is QITLI. This is V under HIT QIT LI. Now this is what? This PT. So this is VPT. So this is equal to 0. And that means now there is an element here in VI which is not 0. And 0 not it's W belongs to VI. Implies that VI cannot be 0. VI cannot be 0. For any I 1, 2, and 2. Okay. So this is what we have proved. Let me see what the time is now. Time says that time is already over. Anyway, so we shall take up this theorem tomorrow morning. So thank you very much for your kind attention. We meet tomorrow.
Thank you, sir.